Okay, let's get started. Howdy. Okay, welcome back to our Ethan 766. So today's contents have a lot of subtopics. Not that they are super important, but I think for your completeness of the knowledge, I thought it's worthwhile including them. And also we get a chance to talk about integer programming after linear programming, so I thought that was useful. But before going there, let's remind ourselves. Last time we talked about integer programming. So did anyone see anything that's missing in this diet problems formulation? No complaint?
There must be other constraints, I guess.
Pardon me?
There must be other constraints because when I saw this problem on Google, there were multiple other constraints as well.
So what are missing constraints?
Can you look at the problem statement and then
Could you speak a little louder? What shouldn't be negative? The decision variable, the xi, is the daily amount of the food I. So that is non-negative. Is that right? Good. So this x is non-negative. So that's one thing to add. Okay. Another thing we're asking is, again, remind yourself about this general formulation. Minimize C transpose X and subject to A X bigger than or equal to B. I let these sign constraints, non-negative constraints, to be part of A. And let's say X belong to n dimension and A belongs to m by n dimension. So we were saying that conceptually we could traverse the extreme points, right? We could traverse the extreme points. In the worst case, the last extreme point, if we don't repeat, the last extreme point in the worst case is a global optimum, right? So that tells us what concept of an algorithm. Time complexity of the algorithm, right? So last time we were asking, well, if that's the case, right, how many extreme points or vertices are there for this polyhedron? By the way, if the polyhedron is bounded, then it's called a polytope, right? So how many extreme points or vertices are there if we need to figure out the time complexity? Let's say there are m constraints and the decision variable is in the n-dimensional space. How many extreme points? Anyone? How do you get a vertex or extreme point? What do you need? Needs what? Intersection of some number of equality, right? Equalities, right? So in the terminology of optimization, we say that that constraint is active, meaning that it's strictly equal. Like, you know, the ice constraint, inequality, happens to be active. So it means equality. So that means some number of equalities needs to be simultaneously held so that we see intersection or vertices. Question is, how many? How many inequalities need to be simultaneously held so that you get a vertex in the n-dimensional space? But in the two-dimensional space, it's easy to see it's 2. In n-dimensional space, how many equalities needs to be held? N. Is there any requirement for this n constraints? Right, they shouldn't be parallel or correlated. In other words, they should be independent from each other, right? So apparently, m has to be bigger than or equal to n, otherwise the system, is underdetermined, right? So in this case, we need at least, out of m constraints, we need exactly n independent inequalities to be active so that we can get an extreme point. So in total, m choose n, assuming that m is bigger than or equal to n, right? Then you can rewrite it as m factorial divided by m factorial divided by m minus n factorial, and then if you use the Stirling formula to approximate m or n factorial, you'll get some approximation of exponential terms. So that's another follow-up, okay? Okay, now let's start today's content. As I said that there are a lot of contents today. Some of them I'm telling you for the completeness. Some of them I think more important as we continue from linear programming to integer programming. You see that the ability to formulate a problem is very critical, okay? We'll see a formulation at the end which is very difficult even to read. Then you wonder how you come up with that, right? Let me remind you where we are. We are in the classical protein structure prediction problem. We are in the safe zone, very safe. What do I mean? What I mean is that there are template sequences who are so similar, more than 30%, that we are almost sure that their structures can be directly borrowed. Okay, this is called a homology modeling approach. There are 2 subproblems that we are talking about. One is, if we know the template, how do we know what positions or residues of the template sequence should be aligned to what positions or residues of the query sequences, so that we know which part of the template structures can be directly borrowed, which part needs to be inserted or deleted or modified. So that was our question, right? So that problem is essentially a sequence alignment problem, and it's solved by dynamic programming. It's exact. And the time complexity and the space complexity are in the order of m times n, right? That's the Needleman-Wunsch algorithm. So since more people are here, we actually have assigned the first homework. So you can check on Canvas. It's under the module for this week. You will have 2 problems in that homework. One, the first one is to get familiar with the PDB format, the structure data. And I'm asking you to plot by yourself the Ramachandran plot and see the different amino acids patterns are different and explain a little bit why you see such pattern difference. The second question is implementing the Needleman-Wunsch algorithm by yourself and align 2 pairs of sequences, okay? And tell which ones are more similar to each other. So these are the 2 homework questions. And you're going to submit the homework in PDF or .c or .py directly on Canvas, okay? So if you have any other questions, please let me know. I will also send another announcement through Canvas. Did I say e-Canvas? Canvas. And you will get an announcement as well, okay? Any questions? You have 2 weeks to finish the 2 questions. Should be relatively straightforward implementations of the algorithms, okay? So today we have 2 parts. The first part is we're going to finish the safe zone by looking at the second problem. Because once we know what's the template, we can do the alignment with order of n squared, right? But where do you find the template? So we're talking about the template identification problem, and this approach is basically a database search, okay? So for a lot of methods, I'm talking about, I'm not asking you to remember what they do, but I'm asking you to sort of not observing how they are done, but actually think about why they are done in that way, because this is a perfect training examples for you to do your own algorithm development, okay? So in these cases, I'm going to mostly, help you think about how you should address these problems algorithmically, okay? And I put in the squared bracket that I'm going to give you additional slides if for some of you who are interested in how to do the whole homology modeling business, I have the additional slides already included, but they are with these squared brackets to show that they're optional and for your completeness of knowledge, okay? Okay, so, and I also put, if you want to know more, chapter 31 of Gu and Boon contain this information. Okay, now here we are. We're first right here, okay? So this is a classical structure prediction, and the rationale is how much we can leverage homology data. We know that in the safe zone, we can leverage the template structures because their sequences are so similar, okay? So let's talk about template identification problem. So what's the problem? You told me that for any given template sequence, I could use Needleman-Wunsch algorithm with a decent time and space complexity and find their optimum alignment. Well, why is there any question that remaining? I can simply apply the Needleman-Wunsch algorithm to every pair of template, potential template, and the query sequence, right? If you have a million templates, I just do it a million times. Why is there a problem?
Sequence length is too much. So.
Sequence length is too much. It's in the order of n squares. Yes, when n is large, this could take minutes or hours evenly, right? But more importantly, the database is large, right? So even we're talking about 180,000 structures, but if we remove the redundancy in the sequence or structure space, we may still talk about, 10 to 4-ish structures. So doing that 10 to 4 times, right? This hours or tens of minutes is still not an idea, right? You think about it, every day, this NCBI BLAST, this web server for sequence alignment, accept how many queries do you know, right? So you cannot even sustain that kind of service. So that means this naive approach, just by enumerating all the pairs, is not possible anyway, right? If you think about how we smartly improved the sequence alignment, we also avoided enumeration, right? We avoided enumeration. We figured out that we can break the bigger problem recursively into smaller and smaller problems, right? And the bigger problems optimal solution can be built upon the smaller subproblems optimal solution. That's how we figured it out, right? So similarly here, we can do something similar as well, in the sense that we don't try to enumerate, but we know when to pay attention and when we can throw away such candidates for templates, right? So how do you accomplish that? The general idea is that you are looking for a fast but heuristic. By heuristics, what I mean is that it doesn't really guarantee you the accuracy. Okay, you will have to sacrifice some accuracy, but you're going to gain the speed. Okay. So how do we really? Yes, we can gain speed, and by sacrificing a little bit of accuracy without guaranteeing the best template and the best alignment with that best template. But what can be done? Well, if you think about a database of templates, maybe 10 to 4, maybe less than 0.01 or 0.1% of the templates are really valid template candidates, right? They are very similar probably. Most of the time you are doing what? If you take the naive approach, 99.9% of the pairwise alignment by dynamic programming is wasted to very dissimilar sequences or regions that are very dissimilar. So that means somehow we have to tell that those majority, 99.9%, are dead ends. that we can throw away. And we need to figure out that there are dead ends before we do the complete dynamic programming. Is that right? So that's the idea, okay? Or in other words, if you don't try to figure out which are dead ends, you can also inversely figure out which ones are really promising and only focus on those. Either way, right? So how do you do that? The idea is, is very simple. The key insights is that, if two sequences are very similar to each other, if we are talking about the global pairwise alignment, they must share some substrings or subsequences that are very similar or identical. So that's a key observation, okay? So that's why if you talk about, the most cited papers in the last century or even until the first 10 or 20 years of this century, one of the papers is this tool, BLAST, for basic local alignment search tool. As you can see from the name, it's a database search tool, and it's for local alignment. As long as you have some subsequences or regions that can be identified, commonly shared, then that's fine. So that's first developed actually more than 30 years ago. It's one of the top 10 most cited papers. So what it's trying to do is first, we try to compile a list of words for query, and then scan the sequences in the database for hits. So if they see whether this potential candidates for templates contain those words, okay? If they do, that's a hit. Then you gradually extend the hits from the shorter sequences or words gradually into longer and longer words, right? Because you are trying to do the local alignment. You try to find the bulk of regions that are similarly shared, okay? So again, this is very simple ideas that, I thought in general, this is something that quite classical approach, right? What you do is first, as I said, if you have a query sequence, you can break them into words, like a k-mer, here k equal to 3, right? K consecutive letters, right? And they could be overlapping, right? And then these are words, right? In the meantime, you can also break the database sequences into words as well, right? Then you are basically querying these words, right, in the database to find whether there's a hit, right? So scanning for hits is a relatively classical problem. What they are trying to do is basically compare two word lists. One is a query word list and one is a database sequence, database word list, right? And you try to find the occurrence of a list of words in a sequence, right? This is a classical problem, right? When people first try to study, literature from a statistical point of view, they try to see what words are used at what frequency by Shakespeare versus others, right? And these, what approaches can be used? You can use hashing, right? This is a very classical algorithm, or you can use a faster algorithm such as deterministic finite automation or finite state machine, okay? Once you figured out that, these query words do have hits in the template sequences, then what you need is, grow these short words into longer and longer regions, right? This is called hit extension. So you want to extend these words on both sides, right? For instance, you may have a 4-letter word, SRSK, being shared between the query, between the query words and the database words, and this is a sequence from the database that contains that query words. Then you want to see whether I can grow this word in two directions so that this matching can be extended. For instance, I can go this direction by extending from K to G, E, P. Then I realize that, this is perfectly fine for the query sequence as well, right? So I can extend this word left or right to make it longer, right? Eventually I figure out that this is the maximum segment. Why do I care about the maximum segment? That's because I'm doing the local alignment, not the global alignment. I'm interested in the commonly shared subregions, okay? So another one is called SciBLAST. BLAST is able to help you, remember, it's a fast heuristic. It helps you find the homologs, but it could miss something, okay? So SciBLAST makes sure that even if the homology or the relatives are distant, you can still find those distant homologs. That's what SciBLAST is doing. But the reason I'm introducing SciBLAST, it contains another layer. That is, I want to tell you something called profiles or position-specific scoring matrices, or profiles. This concept is very important as we step away from the safe zone to the twilight zone, okay? So this is called the position-specific scoring matrix. So in the homework, when you do the pairwise alignment, you're not going to use the +1, -1 simple scoring matrices. You're going to use something called Blossom 62. I introduced this with a slide, but I put a squared bracket so you can read that. But you can also download this Blossom 62 for the substitution matrix, right? What is the difference or similarity between A and G, or T and V? These are amino acids, okay? So what SciBLAST is better at than BLAST is that it's more sensitive, okay? So it's not using the predefined scoring matrices like Blossom 62. It's actually building a position-specific scoring matrix specifically for the query protein, okay? So in the case of BLAST, it's always using a fixed, predefined scoring matrix like Blossom 62, right? The similarity between A and G is always the same. But in the case of SciBLAST, it builds a position-specific scoring matrix, okay? Specific to the position, specific to the protein family. I will talk about it. So this means it's more sensitive to find distantly related sequences that are often missed in the BLAST search. So what is a position-specific scoring matrix? Well, you can think of it as some kind of probability mass distribution, okay? So previously you heard about the notion of describing a sequence, in this case, a nucleotide sequence, as a sentence written in a lot of letters, right? So at each position, you have one letter. So in some sense, if you regard each position not as a fixed letter, but regard it as a random variable, which can take 20 plus 1 values. That 1 is the gap, that 20 is amino acid. Then you can think of each position contains a probability distribution, right? If you use C and G and disregard the other possibilities, then you have a probability that is, if it's ACGT, then it's what? 0, 1, 0, 0, right? And then this is 0, 0, 1, 0, right? So just, there's a 100% for some letter, right? But what if you can change that, right, into a distribution? It's not like a single letter is taking 100% probability. The way you do it is constructing a profile like the following. You first do a multiple sequence alignment. Okay, you may say, well, wait a minute, you told me what is, pairwise sequence alignment, right? And now you're talking about a multiple sequence alignment. So how do you do that? So you can do it in different ways. The slide that I skipped, you can do a lot of pairwise and then stack them together, or other ways, right? And there are tools for you to do that. Once you do the multiple sequence alignment, you basically put a family of homolog sequence together in the aligned way. Okay? So every position is aligned. And then you can count for each position what's the frequency of every letter, right? Right? And then, if you're looking at CG hyphen, for instance, right? And we are looking at the position, so for every position, right, we have a scoring matrix, right? In this case, for instance, for column J, right, is a position J, right? And I is the amino acid or nucleotide, right? So there are 20 plus 1 or 4 plus 1 in the case of proteins or in the case of DNA, right? And the number of columns, or J, is the number of positions, right, or length of the protein. Then we can calculate the frequency Fij based on the simple observation statistics, right? Every column, there is a frequency, right? They add up to 1, okay? Then we have to do one thing, right? We have to normalize that frequency, because you see here that, oh, there is a 75% and there's a 25% here. Is it high or is it low, right? By looking at the absolute frequency at this position, we have no idea, right? So we can normalize that frequency, which is position-specific, J-dependent, by a background frequency for this amino acid I, regardless of position J, okay? So you can look at all these families. For instance, we have a lot of A, 1, 2, 3, 4, 5, 6. There are 6 A's here. So A is already overrepresented in this family, right? So seen like at some position, A contains, constitutes 75% or 50% is not a big deal for this family, right? Right? So in this case, you normalize the frequency observed, position-specific frequency, by the position, independent background frequency for that amino acid. And then you take, this is called what? Odds, right? Right? Frequency divided by the background, right? That's called the odds. And then you take a log. This is a log odds, basically, isn't it? Right? So I didn't talk about the slides, for instance, how the blossom or PAM is constructed. That's also very similar. They also use log odds, but back then, they didn't consider the positions and so on, okay? So in other words, now you can think of this protein sequence not as individual protein sequence, but it's not like every position you have a single letter. It's not like every position now you have a probability distribution over 20 plus 1 letters if you are in the world of proteins, isn't it? Right? So this is called the profiles. It's sort of generalized sequences, okay? It's not saying that what is the letter at position 1 or 2 or 3 for this sequence, right? It's actually reflecting what's the chance of the letter A, C, G, T at each position given this family, okay? So that is what the profiles means. So profiles are generalized compared to sequences, right? It's, a distribution instead of the fixed points. That's the big deal, okay? So then how do you use the profiles that are supposedly more sensitive to discover the distant homologs or relatives? It's very simple. Let's regard like there is a, some kind of three-dimensional mapping of a protein universe, okay? They map it through the alpha, beta, or alpha-beta structures, okay? Then imagine that you start, with some kind of query sequence here, okay? And then you look around, right? Build a multiple sequence alignment, and first of all, at the beginning, you have no idea, okay? You have no priors. The only prior for your scoring matrix is probably Blossom, right? You can use Blossom 62, that is position independent. Then using the Blossom, you look around and this circle basically tells you what similar sequences you can see, okay? You will miss some remote homologs, right? You will miss some remote homologs, but very close homologs will be seen here, for instance, okay? Once you have accumulated the initial family, now you can build profiles or position-specific scoring matrix based on this, right? You will replace Blossom 62 now by the first step profile. And then using that new scoring matrix, maybe you are able to find these more distant homologs in step 2, right? Now you expanded your family, right? From step 1 to step 2, and you can update your scoring matrix, which probably allows you to find even more distant homologs going this way, right? In the end, you probably are able to find the whole protein family for that query sequences. So that's what the iterative search is for. So if you think about what SciBlast is called, right? SciBlast is called position-specific scoring. PS stands for position-specific, and IS stands for iterative, okay? So position-specific tells you they are using profiles instead of family-specific profiles instead of the predefined blossom. And then this profile is actually iterative, okay, updated. So that's what SciBlast is doing, okay? So if you're interested, the sequence comparison does not always have to be based on alignments. There are alignment-free methods if you're interested in them. And sometimes you may desire to do that without alignment, and the problems, the reason of doing that without alignment are listed here. So if you're interested, I list this in the slides for completeness. Bless you. And I also give you the whole appendix because now I have introduced the 2 key questions in the safe zone, right? Finding the template using the database search, including SciBlast, and then doing the pairwise alignment between the identified template and the query sequence by using dynamic programming. Then in the end, you are able to build the structure because that's your end goal. So I give some additional slides if you are interested in, right? So again, we follow the order of database search, and then we find a template, and then we align, and the refine the align, and then the common parts are taken from the structure, right? But then we have to insert loops, right? That's an insertion, or delete something, or refine the structure all over. And there are tools for you to do that. Again, these slides are included for completeness. For those of you who are interested in it, you can take a more look into these, okay? Okay, so with this, I'd like to finish the first part. I think we're done for the safe zone, okay? So in the safe zone, we see that we are solving these 2 kinds of problems, right? The problem that remains is, we know the steps that we identify the template, generate the backbone based on the identified template structure and which portions are aligned, and then we insert the loops and we add the side chains on top of the backbone. We optimize the model and validate the model, including Ramachandran plot, right? What problem remains? The problem is that the safe zone is safe. It's easy to operate. But the problem is that the safe zone is too small, okay? 75 to 35% of the genomes are estimated to be outside of the safe zone, okay? It's a wide estimation from 75 to 35, up to 75%, okay? There's no accurate estimate, but up to 75% of them are not operable in the safe zone. So the safe zone is too small. So then we have to go beyond that. In the twilight zone, right, the sequence similarity is high, but not high enough to enable the homology modeling. We are doing the threading, right? We are saying that these similar profiles must have similar folds, rather than saying that the similar sequences must have similar structures. They are not that similar sequence, but they are similar in the generalized sequence called profiles. So then they have similar folds rather than similar structures, because structures are more unique compared to the folds. When you have, when you are in the ab initio, when you are in the midnight zone, when the sequence similarity of the most optimistic case is so low, then you probably cannot use template at all, and you have to use ab initio approach. Okay. What AlphaFold and other methods have revolutionized is how we view the problem, actually. Because at early days, we think that we need a global sequence homolog, then we borrow their structure. Then threading and other methods tell us that we can break them into fragments and use naturally observed fragments and assemble them. So at the fragment level or at the fold level, they are still similar, right? But what AlphaFold tells us is that there are other less apparent patterns that can be discovered by these deep learning models. So the similarity probably is no longer defined by what we are looking at, for instance, sequence identity. Okay, I think that's what the revolution is about. Okay, back then, the whole three scenarios are based on our observation that if sequences are similar enough, more than 30%, then their structures are similar. So that guided all these developments, right? But apparently, more advanced models may be able to discover less visible or apparent patterns that can be utilized. Okay. So now, and there are a lot of structure prediction efforts using homology modeling or beyond, right? For instance, when the outbreak of SARS-CoV-2 in the early 2020, so a lot of efforts were paid, and there's some illustration of using BLAST, using PDB, using PyMO, using homology modeling, and do some drug discovery. It stopped update probably later that year, but it's a great showcase of citizen scientists or cross-discipline scientists, right? So you can see how you actually use this for discoveries in a difficult timing. So now I'm moving on to part 2. Any questions before I move to part 2? Okay, now I'm moving to part 2, okay? We said that previously in the safe zone, if the sequence identity is so large, more than 30%, they almost guarantee the similar structure. So I can use homology modeling. I can break them into 2 optimization problems, and using dynamic programming or heuristics like SciBlast, okay? Now, we're entering the twilight zone when the sequence identity is 20 to 30%, okay? The difficulty here is that you may have a lot of templates whose sequences are 20 to 30% identical to the query sequence. But some of them have very similar structures to the query protein. Some of them have very different structures to the query protein. By just looking at the sequence identity, you have no idea which one is of similar structures or which one is not. That's a problem, okay? So in other words, the sequence identity signal is not enough to tell us in a high resolution whether structures are similar. That's a problem, okay? The sequence level signal is not high enough. It's too low to sustain the structure similarity, right? So we're going to talk about how to solve this problem. I'm going to ask you a question, basically is, what can we do? What can we do, right? What can you do? Data, principle, what can we do with data? You either use new data or additional data, or use your old data more smartly, or both, right? That's all you can do with the data part, right? Right? Of course, your model can be accordingly modified and so on, right? For the principle, you of course, can use that to guide the design of the model and so on, right? So I'm asking you the following question, right? In this case, what data hasn't been used and can be used? Let's start with the earlier question. What data has been used so far? In the case of the safe zone homology modeling, what data has been used? That's the criteria. What data has been used? So you have a query sequence, right? And you have what? A database of potential, a sequence database of potential candidates. Potential candidates for the template, right? And then once you figure out the template, you're going to use the structure of that identified template, right? Right? Did you smell something that hasn't been used so far? Is there anything that we haven't used? Let me remind you, for the template library, we compare all their sequences to the query sequence in the fast heuristics. Once we figure out some good candidates, we're going to borrow their structure. What data hasn't been used so far? Structures of what? What data hasn't been used? We used the structures of the identified templates. Did we use all other structures? We threw them away. Because back then, we didn't need the help of those structures. We just need sequences, and the signal is clear enough that if it's above 30% similar, we just look at that sequence and that structure, right? We never needed, back then in the safe zone, additional help. We just threw away those structures who are potentially different or who are not necessarily the ultimately identified templates, right? So that's how you can solve the problem, actually. Okay? So we're going to talk about, again, two subproblems, very similar to the safe zone. First is, in the safe zone, remember, we had to align a query sequence to a template sequence. Now, we're going to align the query sequence to the template structure or folds. Okay? This is additional data we never used. Okay? And it involves integer programming and linear programming. We're going to talk about them briefly. And then similar to the safe zone, right? I was saying that once you figure out the template folds, right, you just align the query sequence to it. But how do I find the folds, right? You know, I know there are only 10 to 3, right, folds, much smaller than 10 to 5 or 10 to 180,000, 10 to 5 structures, right? I know it's much smaller number, but still, can I, figure out which folds are the best? It's like the database search problem we were talking about, right? So that problem is more solved by machine learning nowadays. You start with a sequence, you predict which one of the 3,000 folds it belongs to or give a probability matrix. I put it in the light gray to just say that I'm not going to talk more details about it because I will finish the structure prediction problem and talk about the numerical optimization. Then I will start talking about machine learning using protein function prediction. Okay, so that part I will not emphasize. So now let's start with our twilight zone. Okay, what's the motivation here? There are two observations that lead to the so-called threading algorithm in the safe zone. One is the fact that we showed before, over the years, right, you look at the new folds every year or in blue, or the cumulative growth in red, we sort of see a saturation, right? There's a small number of protein folds, seemingly, which summarize the pattern of the secondary structures in the structures, right? That number is small and seems to reach a saturation. So that's good. So I may not know exactly what's your structure, but the next best thing is probably its fold, right? It's like the pattern of the structure, okay? So with that observation, we talk about the twilight zone. The method is called threading. Exactly is what I'm trying to say here is that what additional data can you use? We previously did not use any potential template structure except the templates we eventually identified, right? So the additional data is the structure information in the database, okay? So in other words, if there are only 3,000 folds, right, in nature, and most likely we have seen all of them, then we can ask, can we kind of look at the query sequence, right, and regard it like a string or like a string, and then if we have like 1,000 folds, can we thread the query sequence to each of the fold and see how the query sequence like the fold or not, or how much they like it, okay? So that's the threading. In other words, you are aligning not two sequences, but you are aligning the target sequence onto the 3D structure. In this case, it's one of the folds. Any question? Any question? So this is the additional data we are using, and the way we use the data is try to align the query sequence, right, like to thread the sequence onto the structure, and there are 3,000 of them. And then we can figure out whether the sequence is a good fit to the structure based on the local structure, environment, and pairwise interactions. These are like the objective function that we can talk about later on. Okay? So we said that, you may wonder, why can I use BLAST or SciBLAST to find the fold, instead of doing it for all of the folds? The problem is that, even SciBLAST is better than BLAST in discovering the distant homologs, but in our case, we are in the twilight zone. It's even a tougher, okay, situation that SciBLAST is not perfect. Okay, any question? Okay, with this idea in mind, then what remains to be done is how we align a sequence to a structure. We know how to align sequences, right? How we align to a sequence to a structure, right? What are your thoughts? What's the first thing you have to do is to represent the structure in some way that is friendly to be aligned to a sequence. Is that right? So, let's talk about threading. There are three key components of threading, exactly the three for optimization. Decision variable, objective function, and search algorithm, okay? The decision variable, just like the sequence alignment, is about which residue in the query sequence to align to which position or residue in the template fold, right? This is the decision variable. Related concepts or barriers you have to overcome is how do you represent the query or the target, right? A sequence or profiles or more that you have learned, right? And you may eventually use a different algorithm, but you have to start with the representation of the target. Then you need to have a library of template folds, and then you have to represent the template folds as well, right? Then you align the representations of the target to the representations of the template, of the target, right? The objective function is to make sure that the sequence is a good fit to that structure. So it will, it will involve some scoring that we'll talk about. And lastly, among all possible alignments, right, which ones are the best? That's the search algorithm. We already knew from the sequence alignment that we cannot afford brute force enumeration, which is, giving us astronomical combinations, right? Okay, now let's follow these three elements and start with the decision variable, okay? Remember that to do that, we have to represent the query or the target sequence as well as the template folds. Okay? So, how do you represent a query or a target? The easiest way is just look at the sequence alone, right? Just string. But you have learned something more than that. You can use the profile or the position-specific scoring matrix derived from multiple sequence alignment. You can look at the profile instead of the sequence. Okay? It's not like a fixed point for every position, but a random variable with a distribution, right? Probability mass distribution. You can do more because now you are aligning a query sequence to a target structure, right? You can figure out, for instance, starting with a template sequence, what is the predicted secondary structure in 3 classes or 8 classes. Remember, we talked about this problem before. One of the earliest application of machine learning in structural bioinformatics is predicting from the protein sequence the secondary structures, right? Remember, neural networks was used back then before I was born, right? And then, so you can use that one. And you can also use the predicted solvent accessibility, whether each residue is at the core or at the surface or somewhere between. So all these are sequence, evolutionary, secondary structure, and solvent exposure, right? So these are the different contexts. You have the sequence context. You have the evolutionary context across the whole family. And you have the structural context, whether it's a secondary structure or the solvent accessibility, right? Because predicting the secondary structure is much, much easier than predicting the tertiary structure. Of course, arguably, you can say that predicting the tertiary structure after AlphaFold is easy, but still, right? So potentially, if you're redoing this, maybe you will use the actual structure even. So this is how to represent a target, as I said, sequence, evolutionary profiles, and structural context. Predicted, okay? We only have the predicted, okay? Remember, the query sequence have no structure, right? But the structural context, like a secondary structure or solvent accessibility, very easy to predict. Now, how to represent a template? I first have to select templates, right? To construct a library. So for any library, you need it to be sufficiently diverse, no redundancy. In the meantime, the union of them should be inclusive, right? They should be diverse and inclusive in both the sequence and the fold space, right? What people usually do is, for instance, in this paper, they cluster the entire PDB into the representative families at the level of 35% global sequence identity, right? As you see in the homework question 1, PDB actually gives you such clusters, which are updated on a daily basis. Okay, so getting the template library is done in this way. Once you have the template, you have to represent the template, right? So just like the query sequence, you could have the sequence, you could have the evolutionary profile, and now you have the actual structural context because these templates have structures, right? You can have the actual secondary structure and actual solvent accessibility, right? And you can even do some structure-based profiles, doing not multiple sequence alignment and get the profile, you can do the multiple structure alignment, okay? But if we forget about this, and all these representations here are 1D. By 1D, I mean what? I mean every position is featurized by different features, okay? So I don't have the pairwise features. I only have the feature for every position. It's like a 1D. So in other words, it's 1 dimension for the sequence and 21 dimension for the profiles. And then if there are 3 classes of secondary structures, then that's 3 dimensions for the secondary structure. If there are 3 levels of solvent accessibility, that's 3 again. So the total number of features is like 1 plus 21 plus 3 plus 3, okay? right? But these features are one dimension, right? So if every row is a position, then if every column is a position, then you have 1 plus 21 plus 3 plus 3 rows. These are the number of features you have. Okay, that's your feature matrix. So before we talk about additional representation, now that you know both templates and sequences, query sequence and the template folds can be represented in 1D, right? Do you have an algorithm to align them? Have you learned an algorithm to align them? The only difference is in the past, you only consider sequences. Now you have sequence, profiles, and structural context. Are you able to align them?
We need a score based on sequence structure.
Yes. Let's say you have a score, right? For similarity between different secondary structures or profiles and so on, right? And it's just like the sequence alignment is pairwise additive. Okay, for every pair of positions, we add the similarities together, right? Any ideas?
Yeah, then we can use the same algorithm.
Same algorithm as?
We studied in last lecture. If we have the scores for the similarities.
What struct?
The algorithm that can give us.
Oh, you said BLAST? I see. We're talking about pairwise alignment for now. Yeah, not the database search. But you're right. So let's keep that question in mind, and I will talk about the answer right away, okay? But there's also more information in the template, because the template has a structure. What we have had so far from the actual secondary structure and solvent accessibility is like, if you think about the protein structure, it's like a point cloud, right? What we have here is like a marginalized distribution for every position, right? We are throwing a lot of higher order information. For instance, right? Whether residue I is close to residue J, so-called contact. This is a two-body or pairwise contact, or multi-body, IJK interact in the cluster. Those kind of higher order information than 1D are not considered, okay? So let's also keep that in mind, okay? Because usually when you want to improve your algorithm, you got to be able to rationally construct that, right? Either you use more data or use the data more smartly or both, right? So the second element is the objective function like Salman was asking. And we can do a lot of weighted sums, okay? So again, we are summing over all the aligned positions. For each aligned position, we can do a weighted sum based on the sequence or profile similarity or the environmental fitness score or the structure consistency, like whether the secondary structures or the contacts are preserved. And then we can also have a gap penalty, like what we do in the sequence alignment, okay? So with the decision variable and its objective functions more or less figured out, we have to talk about the algorithm, right? Because we need to overcome the combinatorial explosion. So if you only represent the template by the 1D representation, then you can use the same dynamic programming to align a query sequence to a template structure, okay? It's still polynomial time. You can still use dynamic programming, okay? So this is one of the earlier methods called master. They use dynamic programming. But, so in that case, you can have polynomial time algorithm, right? Including dynamic programming, that's order of m times n, right? Or n squared, if m equals to n. But if you use 2D representations like contact map included, then the problem gets NP hard, meaning non-deterministic polynomial time hard. It's basically a way to define a class of optimization problems. Roughly, you can think of there's no polynomial time algorithm, okay? So if you were in the age of seeing the threading algorithm, including master, you naturally will ask, what information have I not used yet, or what data have I not used yet, so that if I use it, I can improve the accuracy. So I'm giving you one example. What they see is that, oh, the 2D information in the template is not used yet. So I can use that additional information and improve the performance, okay? So innovation is very important to us, but we also have to keep in mind that it doesn't come easy, but there are certain ways to innovate, okay? So there is the scientific way to do science, okay? So in this case, retrospectively, it seems like a great idea, right? You are trying to use more data. You gotta have, if this data is reliable, you gotta have more accurate solutions. And that's exactly what the Xu group developed called Raptor. We're gonna talk about that example. And it's using integer programming, okay? I think now is a good time to talk about integer programming, right? I'm gonna borrow some slides, right? So integer programming, after we learned the linear programming, means that the decision variables are no longer continuous, but they could be, just integers, right? So what does that mean? We know that for optimization algorithm, we usually wonder whether it's convex or non-convex. We know that that's a definition. That's a difference between, easy and difficult optimization problems. So for linear programming, we know that the feasible set is convex and the objective function is convex. So, we have guarantee of the global optimum. Some are slower, some are faster, okay? But in the case of integer programming, do we have a convex problem or not? Let's say the objective function is linear. Everything is the same as linear programming, except that the decision variables are only integers. No longer just continuous real numbers. Are you going to say this is a convex or non-convex problem? Who think it's convex? Who think it's non-convex? Okay. Why? The objective function is linear.
The feasible set is both.
Yes, as Nami said, that the feasible set contains a lot of discrete points. If you connect 2 points, very likely that most of the segment is not in the feasible set, right? So, in other words, integer programming in general is NP hard, okay? So let's talk about the formulation, which can be very interesting, right? So let's talk about how to translate the real-world problems, including constraint, right, into an optimization problem. Okay, in this case, it's a constraint. So if you select x1 equal to 1 if it's iPad, x5 equal to 1 is the course 6.041. 6 is Electrical Engineering and Computer Science at MIT, right, course 6. So if you select the iPad, you cannot select x5. So in other words, if x1 equal to 1, x5 cannot be equal to 1. Okay, so that means if x1 and x5 are either 0 or 1, right, out of the 4 combinations, or the 4 points in the feasible set, the one that's not allowed is this point. When x1 is equal to 1, this is 1, x5 cannot be equal to 1. So how do you formulate that constraint? Our decision variables are x1 and x5. What is the constraint that can express this constraint 1 in plain language. Let's translate the plain language to mathematical formulation. Anyone? Pardon me? Sum should be less than what?
1.
Less than or equal to 1. All right? Because when both are 1, the sum is 2, right? So basically, it has to be on lower left of this green line. x1 plus x5 is less than or equal to 1. By the way, I ignored x1 and x5 being binary in all these slides, okay? This is by default because it's integer programming, okay? Let's look at another example. Let's have price 1 and 2 being x1 and x2, okay? If you select x1, that means if x1 equal to 1, then you must select x2. It means if x1 equal to 1, x2 has to be equal to 1. So in other words, out of these 4 choices, this one is not allowed. When x1 is 1, x2 is 0, that is not allowed. Because when x1 is equal to 1, x2 has to be equal to 1. So this is the only feasible solution for x2 when x1 is equal to 1. Now, can we rewrite the constraint mathematically? Again, you can pay attention to this green line. Make sure that we have to be above this green line instead of below. Anyone? Subtraction. Which minus which? Yes, x2 minus x1. Less than or equal to, bigger than or equal to something? This line is x2 equal to x1, right? So if you're above it, that means it's x2 bigger than or equal to x1. As you said, x2 minus x1 is bigger than or equal to 0, right? So you notice that these constraints are linear, just like what you see in the linear programming. But the only difference is that you have the additional constraint that x1, x2, or these decision variables are integers, or binary in this case, okay? If x1 and x2 are between 0 and 1, then it's linear programming, okay? Easy to solve. Now, last one. You must select one price or both. You cannot select none. In other words, you cannot let x1 and x2 be 0 at the same time. I think everybody should know now after seeing. Let's see. Do you want to give it a try? So the hint is that we have to be above the green line. Yes. Pardon me? Exactly. Equal to 1, right? So x1 plus x2 should be bigger than or equal to 1. You want to be above that line, right? It's really fun, right? So if you want to explore more, you can check this link. Actually, I just gave very simple examples, okay? But I also have to emphasize that you could have other kind of formulations, but these ones are good because they are linear, okay? Right? Okay, now let's talk about how Raptor introduced the additional information of 2D contact and do the threading, aligning the query sequence right up here, okay, to a template structure, okay? So this is the template structure and the query sequence, okay? So we can, first of all, only look at the core, which are the stable secondary structures, alpha helix and beta sheets, and we can ignore those loops because the loops are less defining folds, Okay, the secondary structures, stable ones, so the consecutive ones are called the cores. We also know that the pairwise interaction between the cores, right? If the two cores are close, then we have a solid arc. That's the additional information in the template structure we wanted to use. Otherwise, we can just do the dynamic programming, okay? Okay, so that is a blessing, but that's also the challenge. Okay, let's keep that in mind. Then we have the sequence, okay? The query sequence, and then let's assume that, for instance, the core 1's first position is aligned to this position. Then the rest is very simply following that. We just have the next few up to the length of the core 1, right? So that is a very simple alignment, right? This blue line is alignment of a core position to a sequence or query position, okay? Core of the template to a position on the query sequence, okay? Now you see these dashed arcs. What are the dashed arcs? The dashed arcs are essentially very similar to the solid arcs in the template structures. In the query sequence, we don't have structures and we don't know the actual context. But we are saying that if this query sequence feels okay to fold into the fold like this, then its 2D contact should resemble the solid arcs observed in the template structure. So if that's the case, for instance, there is a contact between core 1 and core 2, and I know that core 1 is aligned to these positions, and core 2 are aligned to these positions, then I will have an interaction between the residues across the positions aligned to core 1 and core 2 respectively. Okay? So that's a dashed line. It's hypothetical. Okay? So basically we are saying that we're going to use this additional information from the template. That's 2D. And we think that we're going to see whether enforcing the similar 2D pattern in the query sequence is a good thing or a bad thing. Okay, we're going to use optimization to find the best way to align. Remember, these blue ones, these assignments, are not fixed. Okay, these are our decision variables. Where to place the blue ones are our decision variables, right? And the dashed arcs enter the objective function. Okay, it will also show in the constraint and the objective function. Okay, so let's see. Well, our decision variable xil is binary. It's 1 if and only if core ci is aligned to target position L on the query sequence. Okay? So, for instance, this is core 1 aligned to position L here. Okay? When I say that a core is aligned to a position, I mean that the head of the core is aligned to that position because the rest just follows. Okay? So let's not get confused. When I say the core is aligned to a position, core is on the template, fold, or structure, it means that the head of that core is aligned to that position because the rest just follows. Okay? That is our decision variable, right? We want to figure out the head of each core is aligned to what positions. And there's another decision variable because we have to address this arcs or the 2D contact, okay? So if core CI1 is aligned to target position as L1 and I2 is aligned to position L2, we have a Y, which basically gives the binary variable for the arc, okay? So if I1 is aligned to L1 and I2 is aligned to L2, then this, YI1, L1, I2, L2 could be equal to 1. Okay, so this is a familiar integer programming formulation like one of the examples we have seen, right? In other words, only if core I1 is aligned to position L1 and core I2 is aligned to position L2 could this Y be 1. This Y is the arc, okay? Now, the formulation is First, the objective function is relatively easy. I don't want to say too much about it. It's a weighted sum of mutation, fitness, secondary structure, and so on. And